application of integration is to take a region and revolve it around an axis. We take a region in a plane and revolve it around an axis or a line. And when you do that, you get something that's called a solid of revolution. So if we take a look at a coordinate plane here, and we go ahead and put a region here. So we'll go from point A to point B. And we take this region and revolve it around the horizontal axis. We get this solid, this three-dimensional solid that looks something like you would get if you would take this and clone it and flip it. Over that horizontal axis. And so you'd get this. You get this three-dimensional circular solid that has kind of a scalloped outer surface to it. And so if we take a look at this from a Riemann sum standpoint, we could divide that region into rectangles and add up the rectangles. And so if we take a look at a representative rectangle, so if we took a look at a section here within this area, and that differential width is our dx, or our delta x, and the height of this rectangle goes from the axis up to the function here, so this height ends up being the value of the function at x. Then if we take this rectangle and spin it, we get what we call a disk. And that disk is nothing more than a short, stubby cylinder. And so to find the volume of that incremental disk, which I'm going to call delta volume, we're going to take the area of the base. And that base is circular, so it's pi times r squared. And we're going to multiply it times the height of that, which is our delta x. And of course, this r here, that distance, is the radius of that cylinder, which goes from the axis up to the function. So there's our radius. And like we said, that distance is nothing more than the function. So this incremental volume then becomes pi times this function, f of x quantity squared, delta x. And so that gives us that incremental volume for that rectangle. And of course, if we add up all the rectangles from A to B, we'll get a Riemann sum for an estimate of volume for that solid. And if we then take that Riemann sum and take its limit as delta x goes to 0, then we can call that that volume from A to B. We can use an integral from A to B, and so we take that function and square it, and the delta x, which is the thickness of the incremental rectangle here, just becomes our differential dx. And so we have an expression that gets us the exact value of that volume as we integrate that from A to B. And that is shown right here for our horizontal axis of revolution. Notice that when we have a horizontal axis of revolution, we have a delta x along the horizontal axis. So we need a function that is written in terms of x. We need a function here that's written in terms of x to match our differential expression dx. If we have a vertical axis of revolution, where we would revolve it around the y-axis or a vertical line, then we're going to have to rotate our incremental volume, which means we need a function in terms of y, and we need a differential expression in terms of y. Looking at this example, we have the function y equals 4 minus x squared, and we want to rotate that about the x-axis, and we're looking at the region from 0 to 2. So if we take a look at the function here graphed, really what we're doing is we're looking at just this region here in the first quadrant. So we're looking at rotating this region about the x-axis. So a couple of things that I like to do just to kind of to organize my information here is I like to note the axis of rotation. So our axis of rotation is here about the x-axis. And then I want to draw my incremental rectangle and get the dimensions set up on that rectangle. So if we look at that rectangle, that incremental rectangle, might look something like this. We know it has to be a vertical rectangle. We know we need our dx along the horizontal axis. So we can now label our incremental rectangle. So we know this is our dx. And the height of our rectangle is our function f of x. So our height of our rectangle here is our function f of x, which is equal to 4 minus x squared. And we're going to rotate that about that horizontal axis from 0 to 2. So if we set this up then, we have pi times our radius squared. And our radius is our 4 minus x squared, quantity squared. Remember, this is just our function, and we have to square our function. So we end up having something that we have x squared squared. We have to end up using FOIL to expand this if we want to integrate that by hand. And then our differential dx. And we're starting at, in terms of stacking up these rectangles, we're starting at 0, going out to 2. So those are our limits of integration from 0 to 2. Now this expression should be something you should be able to integrate by hand. And the easiest way to integrate this is to expand this by foiling it. I'm going to pull out the pi because that's a constant. We can pull that out of the integral from 0 to 2. So if we FOIL this, then we're going to get 16 minus 8x squared plus x to the 4th dx. So that's the expression we get when we FOIL it. And then as we integrate that, we're just going to integrate that piece by piece. So we're looking at 16x minus 8 over 3x cubed plus 1/5 x to the 5th. And we're going to evaluate that from 0 to 2. And as we evaluate that from 0 to 2, we plug in 2 to each of those expressions, and then we plug in 0 to each of these expressions. And if you notice when you plug in 0, since you have an x in each expression, that whole thing just ends up being 0. So we're going to have pi times 16 times 2 minus 8 over 3 times 2 cubed plus 1/5 times 2 to the 5th minus 0. And as we evaluate that, we have pi times a quantity of 32 minus 64 over 3 plus 32 over 5. And if we combine all these fractions together, and we can do that with a calculator easily enough. If we take our calculator and let's get that calculator back up there. There we go. Take our calculator and we type in 42 minus 64 divided by 3 plus 32 divided by 5. There's the answer. And I'm just going to go ahead and convert that to a fraction. And it ends up being 256 over 15. So 256 over 15 is what this adds up to, and then we can't forget our pi. So we end up at the bottom with 256 pi over 15, and since this is volume, then we know it's units cubed. For this example, we're going to find the solid of revolution, but in this case, we are going to take this revolution about the y-axis. So if we note our axis of rotation here, it's the y-axis. Since we're rotating around the y-axis, we need a rectangle that's horizontal. We need a dy for the width of that rectangle. So if we set up our incremental rectangle should look something like that. And so that incremental rectangle has a dy thickness, and its height is now in terms of y. So we have to take this expression that we have here, and we see that it's already in terms of y. So the height of this radius here that we're going to rotate around to make our disk is going to be our function in terms of y now instead of x. So it's going to be our minus y squared plus 4y is the height of that rectangle. And we're going to take this, instead of doing the whole thing all the way down to 0, what we're really only going to do here is take the portion of this function that is in this area down to the line y equals 1. So it's kind of like if we would rotate this and it would be some sort of M&M shaped piece, we would cut the bottom off here at y equals 1. So what this is doing is it's setting up our limits of integration to be from 1 to 4. So in this case, we're going to define our volume. We can use the expression in terms of y. So our radius of our disk here is minus y squared plus 4y. There's our radius. We have to square that because it's pi r squared. And then the thickness is our dy. And we're going to integrate that from 1 to 4. So from 1, so we're a little bit better, from 1 to 4. And so again, we'd have to FOIL this out. And I'm going to just FOIL it out, but then I'm going to use the integration capabilities of the TI-84. So to FOIL this out, we get y to the 4th. And we get minus 8y cubed and plus 16y squared dy. Okay, so that's what we have to integrate. And again, I'm going to use the integration capabilities of my calculator here. So I'm going to go ahead and go down to fint, that's option 9, and I'm going to go ahead and enter my function here. And my function is y to the 4th. So in this case, I'm just going to use the variable x. That's just the integration variable. So that's not a big deal that that's not a y. So y to the 4th minus 8y cubed plus 16y squared. And the variable of integration, which is y, and from 1 to 4. And if you notice with that fint, that y to the 4th minus 8y cubed plus 16y squared. From 1 to 4, I don't have the pi in there, so that again is just going to get me the portion that that I would integrate. So I have to remember to include the y with that, or the pi with that. So as I hit enter, I get 30.6. So we know that after integrating, I get pi times 30.6. And again, we can take that and make that into a fraction if we want an exact answer. So our exact answer is 153 over 5 times pi.